Hello, I decided to explain the solution of this problem. So flower-like Pseudotree from Codeforces Round 896, Division 2, and also absolve it, so write the code in real time. So let me remind you what the problem is about. You're given a Pseudotree, which is a tree to which one has added exactly one edge. So for example, this is a pseudotree because it can be achieved by adding this edge to this tree. And for example, this is not a pseudotree. And also this is not a pseudotree. Because here we didn't add an edge, and here the initial graph was not connected, so it was not a tree. Also, for example, this graph is a pseudotree. So it is allowed to add an edge which was already in the tree, and in this case it becomes a multiple edge. So we have got a pseudotree, and we know every degree of this pseudotree. So all the degrees are given. And there is an extra condition, which is saying that this pseudotree is flower-like. What is this talking about? It's talking about that there is exactly one cycle, and if we remove all edges from this cycle, there will be several trees. For example, all three trees here are just one vertex trees. And for example, in this case, there is one tree consisting of two vertices and one tree which consists of one vertex. And the flower-like condition is that all these trees have the same depth, so the same maximum length of path from the root to some leaf. So we ask the question, is it possible to construct a pseudotree, flower-like, with given degrees of the vertices? And if so, then provide such tree, such pseudotree. The constraints, which are always part of the solution, part of the statement, are here. So the degrees are from 1 to n, and the number of vertices is at most 1 million. Okay. Actually, the first and the only valuable observation is that most of the time we just need to choose a two-vertex cycle. Yeah, if it's possible to make a two-vertex cycle, then we are fine, because so it is possible to make a two-vertex cycle and make the depths equal. Why is that? This is because there is a flower-like condition, and it says that, for example, if cycle is of length c, then we will get c trees, and all these c trees should be of the same depth. So this is kinda problematic to make the heights equal, the depths equal, if c is big. For example, if c is 7, then you need to make 7 trees of equal depth, and this is kinda difficult. So to not complicate the things, we will most of the time try to make the cycle consisting of two edges. So after that, it is just a case consideration. And actually, I will consider the cases and write the solution at the same time. Okay. Oh no, I think I will firstly explain the solution in its entirety, and then I will write a solution in C++ and remind you of the parts of the solution in the whiteboard which correspond to this piece of code. So, the first thing to do is actually to separate the leaves which have degree equal to 1 and other vertices which have degree at least 2. And also, the thing that is needed to do even before that is to check the sum of all degrees. So, in any tree, you have n vertices and n-1 edges. But if you add one edge and get a pseudotree, it has n vertices and n edges. And so the sum of degrees should be twice that. So, firstly, we need to check the sum of all these and check if it is equal to n. This is the foremost, the first part. You shouldn't do anything before that. So after that, we have checked the sum condition. Now we need to try to do it. So actually, there is an idea which I didn't find while the contest was going, and I read it in editorial, which is to sort all degrees. So let's sort them in decreasing order. And why is that? This is because this order is really helpful in this problem. Yeah, this will add some complications because in the end you will need to construct the graph. For example, assume that you had d1 equals 1, like d2 equals 2, d3 equals 3, I don't know, like this, something like this. I don't like it, though. Okay, let it be it. I think there is no tree like this, but let's assume that it exists. So after the sorting, you will get d1 equals 3, d2 equals 2, and d3 equals 1. And you will construct a graph if it exists. And it doesn't, but we will forget for a while about that. If we construct this graph, it will have degree 3 for vertex 1, degree 2 for vertex 2, and degree 3 for vertex 1, for example. And this is the problem because initially the enumeration was different. So after that, you need to enumerate it back so that this vertex becomes 3, this vertex becomes 2, and this vertex becomes 1. And this process of re-enumeration is it is not very difficult, but it has to be done. So you cannot just sort the Ds. You need to remember which indices were on which positions. And this is important. Okay, so let's assume for now that it is sorted. I will present my way of doing it, actually even without sort. So here it goes. First of all, let's check that. Also one extra idea. The idea, which is also useful from editorial, it kinda not mandatory, so you can solve the problem without noticing this idea, but it really helps with technical details. So it is really important to make this separation of d equals 1 and d at least 2. Why is that? Like if you swap two vertices of degree 1, it doesn't matter at all. It doesn't change the structure of the graph. But if you swap two vertices of degree 2 and 3, for example, it really matters. So what we will do is we will create a skeleton of the graph. It's the positions of these vertices of degrees at least 2. And after we have made the skeleton, it's kinda unique how we add these leaves. It's not unique in the sense that if you have two vertices which like need one leaf, and this vertex, this vertex also needs one leaf. And we have, for example, two leaves with numbers 3 and 7. In this case, we can add 3 here and 7 here, or vice versa. But as I said, it doesn't change the structure of the graph. You can choose the indices arbitrarily. So if you have, for example, six places for leaves and 6 different indices of the leaves, you can match them in any order. Any matching will be fine. So we will just forget about these vertices, and we will add them in the end. So we will have a special function which takes the skeleton of the graph as the input, and it adds all the leaves into the graph accordingly. So we will assume that actually it is S here and not D, where S is number of degrees which is at least 2. So now we have several cases. So the first kind of obvious case. So 0th case is sum of the degrees is not 2n. We have checked that. And if that is true, this is fail. Okay, next case. Now actually some graph should exist. Maybe no, it always exists. It just always exists. Maybe with some multiple edges, but it exists. Because the I is at least 1 for all I. So the next case is... actually, this already means if some case doesn't hold, yeah, so if we have considered the case 0, henceforth we will assume that it is not holding. So after that we will think that sum of the I is 2n. If it's not true, then we can return to the previous case and consider it. So I will draw with green the things that we already know from the previous cases. So now we know that this sum is 2n from the previous case. Okay. Actually, this implies that S is at least 1. Yeah, because if S is 0, then... let me write it here. If S is 0, then all di equal 1. And if all di equal 1, then the sum of di equals the number of vertices, which is n. And this is not 2n, because n is at least 1. Maybe even at least 2. Let me see. Yes, and even at least 2. So as you see, it is not possible. So S is at least 1. Let's now assume that S equals 1. What does it mean? It means that you have only one vertex of degree greater than 1. This is problem, because assume that you have a cycle, and there are some trees rooted on the vertices of this cycle. This implies that all degrees of this cycle is at least 2, because each vertex has 2 neighbors. Maybe it's the same neighbor, but still it is 2 multiple edges, and still the degree is at least 2. So if you have the cycle of length c, then you need at least c vertices of length of degree at least 2. But here we do not have it. Yeah, because here so as I said, c, if c is the length of the cycle, then c is at most s. And here we have s equals 1, so c is also at most 1. So you have a cycle of length 1, and this is not possible. So here we have fail. Simply because it is impossible to just make any pseudotree. As I said, after we have considered the case, we now assume that it doesn't hold. So now we have sum of di equal to n, and s is at least 2. This is what we know now. Okay. So now let's assume that d1 is 2. So the maximum degree of a vertex is 2. This means that all these vertices which we will put in the cycle are of degree 2. And this is kinda easy case. This means that all vertices are of degree 2. And this means that we can put them into one huge cycle. So in this case we say, okay. So we put all these vertices into one big cycle, and actually there are just no leaves left. Yeah, because the sum of degrees should be 2n, and we already have 2n. If we have some leaves, some extra leaves, then the sum of degrees will be less than 2n. So the skeleton will be this cycle, and the graph also will be this cycle. So my camera is a bit laggy. Okay, now we consider the next case. Now, as always, we think that all the previous cases are false. So now sum of di is 2n, s is at least 2, and also we know that d1 is at least 3. What do we do next? I think now we can consider d2 equals 2. And this is also fail. Why is that? So let's look at our cycle. There are two cases. Either all degrees here are 2, or there is a degree at least 3. So let's consider the first case. If all degrees are 2, then actually this cycle is the whole graph. You cannot add anything to it, because since you add any edge here, this degree becomes 3. And we do not have 3's in our cycle. Or at least 3. So this is impossible, because actually d1 is at least 3. So this d1, this vertex cannot be anywhere. It just cannot. So we have a cycle and nothing left. No space left in this device. So this is impossible. The second case is there are some vertices which are of degree at least 3. But there is a problem. Since this is a cycle, it should have some other vertex. And as we know, it has degree at most 2. Because there is only one vertex of degree at least 3. The second is already 2. And this means that we contradict with the flower-like condition. Why? Because this tree will have depth at least 1. yeah, it has one extra child, at least one extra child. So the depth of this tree will be at least 1. But here we do not have any children, so depth is 0 here. This is a contradiction. That's why it is fail. Let's go on. Now we have, sorry, again with green color, I write everything that we already know. Sum of di is 2n, s is at least 2, and now I can write that d2 is at least 3. I don't need to write that d1 is at least 3 because, as we know, d1 is at least d2. It's by definition. That's why I don't need to write it explicitly, but I still wrote it. What then? Actually, now we will consider a pretty huge case, which is s is divisible by 2. This is kinda huge case, and actually in this case the answer is yes. How it is done? We take the vertex which has degree d1 and put it here. Then we have a vertex which is of degree d2 and put it here. We add 2 multiple edges between them. And after that, since s is divisible by 2, all these vertices can be divided into 2 equal groups. Now we add a bamboo here. And, and here. Let me just erase this. We have 2 bamboos of equal length. And finally, we can add children. I mean, this is a skeleton, and if we want to add leaves, we add it here. So actually, both depths will be like, so s half vertices here. Also there is a leaf. So the answer will be, I think, s half. Yeah, because s half minus 1 if we only consider the skeleton, but plus 1 because of the leaves. So the answer is s half, and this is possible. Next case, and in this case, sum of di is 2n, s is at least 2, and since s is odd, we can even say that s is at least 3. Also, s is odd, which will be written like this. 2 does not divide s. And finally, d2 is at least 3. Okay. So in this case, let's consider the next thing, which is d3 equals 2. I assert that it is fail. Let's again consider the cycle. As I said previously, it has to have at least one vertex of degree at least 3, because we have such. And if we have only vertices of degree 2, then the cycle is impossible. We cannot add any other vertices to this graph. So there is a vertex of degree at least 3. The problem is, it cannot now have vertices of degree 2, because in this case the flower condition will be false. Yeah, if this is vertex of degree 2, then this depth is 0, and this depth is at least 1. Okay, so this cycle only has vertices of degree at least 3. And since there are only 2 of them, the cycle is of length 2. And now comes the problem. The only way we can put vertices of degree 2 is to make a bamboo of them. there is no way of branching because they are only of degree 2. They can only have one parent and one child. There is no way of branching it. And same goes here. So if depths are equal, yeah, like this is of depth d and this is also of depth d, then we can calculate s, which is equal to 2 plus 2d. And this is an even number. But here we have the condition that s is odd, so this is impossible. So actually, in this case, we fail because there is no way to make these two trees of same depth. Is it called depth here? Ah, yes, it's called depth, so everything's fine. So in this case, we get a failure. The next case, again, we will write, first of all, our conditions. Sum of di is to n, s is at least 3, 2 is not divisible by s, and d3 is at least 3. Okay, now let's consider some tiny case, which is s equals 3. If s equals 3, then it's kinda easy. We can just make a triangle. And depth will be 1. So we will make a triangle, and all other vertices will be just attached here. So this is possible. Okay. Case 7. Let's again rewrite it. Sum of di is 2n. S is at least 5 now, because 3 is eliminated, and 4 is impossible because of the oddness of the number, or oddity. I don't know. Parity, oddity. 2 is not 2 does not divide s, and d3 is at least 3. What we will consider now is whether or not d1 at least 4. Why is it important? So let's consider like our baseline structure. We have d1 here, d2 here, and we make a bamboo here and a bamboo here. The issue is 2 does not divide s, so these bamboos cannot be of same depth, of same length. But if d1 is at least 4, we can fix this problem. So let's assume that, for example, left bamboo is one edge longer than the second one. In this case, we can move this vertex here and attach it to this vertex. So now we will have 2 equal bamboos, and also vertex 1 will have 1 extra child. And now it is actually working. All depths are now the same. So this is okay case. Okay. Case 8. Now it will be hard to actually write everything that we know. So s is at least 5. 2 does not divide s. And now we know that d1 is 3. But since d1 is 3, d2 is also 3, because d2 is at least 3, but it is at most d1, which is 3. So actually d1 is d2, is equal to d2, and d2 is equal to d3. And they all are equal to 3. Again, it is simple. d3 cannot be greater than 3, because it is at most d1. And it cannot be less than d3, because we already know that it is not true. So now these 3 vertices are of degree 3. Okay. Let's consider now case that d... Let me think. Actually, I think we will consider case that S is at least 7. Yeah? So what do we have here? As we have done previously, we want to use branching to remove one vertex from one of the bamboos and attach it to a branching point. The problem now is that since all these degrees are equal to 3, there is no way to branch here and here. Yeah, there are 2 multiple edges here and only 1 child. We cannot make branching here. But where we can make a branching is here and here. The only problem, let me think, is that if these degrees are 2, then we cannot make branching here. Yeah, because, like, again, this vertex has only 1 parent and it can only have 1 child, so no branching. But since d3 is at least 3, and actually equals 3, we can make branching here. Yeah, we can make this vertex 3, and now it has 2 children. And now this is where the things begin to be good. So again, let's assume that now we have 2 bamboos, and this is one longer than this one. We can remove the vertex from here and reattach it here. And now we have 2 bamboos of equal length. And actually we need it as at least 7 here. Why? Because we need at least 1 vertex here, 1 vertex here, here, and also we need at least 1 vertex here, at least 1 here, and at least 1 here. So 7 is a must in this case. This is kind of hard case, but it is okay. Now if we rewrite it, we have the following. Sum of di equals to n, s is at least 5, 2 does not divide s. Now s is equal to 5. Yeah, because the case of 7 being at least 7 is already considered. And finally d1 equals d2 equals d3 equals 3. Now we will consider the case d5 equals 3. And also d4 always, of course, equals 3. And this is implied. This is also kind of easy case because we can make a 5 cycle. This is the only place where we need the 5 cycle where it is required. And it is easily... so this is a skeleton, and as I always say, we can easily add all the leaves to this Pseudotree. So the answer is okay here. Or yes. And finally, the final case is the 10th case. So as you see, this is kind of complicated problem because of the huge number of cases. S equals 5, 2 does not divide. I kind of don't need 2 does not divide S because we already know that S is 5. And d1 equals d2 equals d3 equals 3, but d5 is 2. This is the final case. Actually, in this case, this is impossible. This is impossible. How do you prove something like this? You just need to consider the cycle. What is the length of the cycle? If you followed the previous cases, you understand that we have a cycle in which all the degrees are at least 3. And this means that we have one of these 3 cases. Either the cycle is of length 2, yeah, because we have 2 vertices of degree 3, or this is a triangle, or this is a square. It cannot be a pentagon because d5 is 2. So one of these 3 cases. This case is kind of already considered... it is not considered, sorry. Still, the answer is no, this is impossible. Because, for example, this is 3, at least 3, this is at least 3. And there should be somewhere the third vertex of degree 3. For example, it is equal to 3. For example, it is here. And it has 2 places to add vertices, and this also has 1 place to add vertices. So we cannot add a leaf here. If we add a leaf here, then this is definitely shorter than this one. So we have to add a vertex of degree 2 here. But now it has a leaf. It can have not a leaf, but what I want to say is we only have now the vertex d4 of unknown degree. And either we put it here or here, the tree which we chose will be of a bigger depth. For example, we chose d4 here, and it's, for example, 2 or 3, it doesn't matter. Then the depth of this tree will be like 3. And the depth of this tree will be 2. The same goes if I attach d4 here. So if d4 is here, then the depth on the left will be 3, because this d4 also has a child. And here the depth would be 2. So this is not the case. This is impossible. Other 2 cases are kinda easier. So for example, in this case, since we have 2 vertices of degree at least 2 remaining, we need to attach them somewhere. But because there are only 2 of them, we cannot attach them to all 3 vertices. So there will be one vertex which only has a leaf as a child. And some other vertex will have a bigger degree as a child, and it also has a child. So there the d will be at least 2, and here d is 1. And finally the square is the same kind of consideration. So there should be a vertex which has no children but leaves, so the depth is 1. And some other vertex has to have a vertex of degree at least 2 as a child, yeah, because d5 is 2. So we have some 5th vertex. And depth here would be at least 2. So we have considered all the 10 cases, and now the only thing that is needed to do is to accurately implement it. This is what I will do now. Okay. This is kinda huge. But it's div2f, so you've signed for this. Firstly, we need to read the input. So I will create a usual multi-test framework. So I read t. Here I just run the function solve test. Okay, what do I do in function solve test? I read n, and then I read all the i's. After that, I will write some function find ans, which will find the answer. I think I will output vector of pairs of ints. Which takes the vector of degrees and returns it. So now we have the answer. And if answer is empty, this will mean that the answer is no. We print no. Is it okay Yes. Otherwise, we print yes. And we print all the pairs. Edge dot first and edge dot second. Yes. Okay, now we need to find the answer. So we will look at the cases and do the thing that is said here. First of all, we need to find the sum of degrees. And this is an important point. You should always look at the constraints. So the degrees here are at most n, so at most million. And the number of degrees is also at most million. So the sum of degrees is at most 10 to the 12th. And this cannot fit in int. So I am sure that if I put them in int, this will overflow and there is a countercess for that. So we need to put long here. So if sum I like can write that this is case 0. So here we just return nothing. I didn't say what n is. Constant n equals d dot size. Great. So now the sum is correct. Now I'd like to make the framework for taking the skeleton of the graph and after that doing the rest of the job. So let's do it. First of all, I write skeleton. Sorry, I'm not sure how skeleton is spelled. I will Google it. Yes, I think I wrote it correctly. Skeleton equals find skeleton of D. So again, if skeleton is empty, we just return nothing. And find skeleton is the same. After that, let's find all actual degrees of the vertices. So how do I do it? First of all, I'd like to have the list of all leaves. So vector int leaves. So if di equals 1, then leaves dot pushback of I. This is the first part. After that, I want to have int. Okay. And also internal vertices which are, sorry. I'll write it like this because internal is actually a keyword of C++. So otherwise, we say that internal vertices dot pushback I. Now we make a vector int of remaining degrees. Which is like D. But after that, we consider all edges of skeleton and subtract 1 from each of its its endpoints. So here we say that remaining degrees of edge.first is decremented, and the remaining degree of the second and is also decremented. Actually, I just realized that I want everything in my solution to be 0 indexed. And this means that here the answer will be with +1s. This is also important. You should, for example, there are several ways of doing it. For example, some people, they just enumerate everything from 1. So they have no v0, a0, or something like this. If they have an array of length n, it is from v1 to vn. I kinda don't like it because there is an extra element v0. Why do you have that? So what I do is, in the beginning of the solution, I subtract 1 from everything which is 1 indexed. So now it is 0 indexed. Now, then I calculate the answer, which is also 0 indexed. And in the end, I add 1 and just while printing the answer. So it's now becomes 1 indexed. So in this solution, everything should be 0 indexed so that you do not confuse any vertex with some neighbor vertex, adjacent vertex. Okay. We have calculated the remaining degrees of the skeleton. Finally, we need to add leaves to vertices which have insufficient degree. And we do it as follows. We consider all vertices. Oh, we consider all internal vertices. And for int j equals 0, j less than remaining degrees of I, we need to add some leaf. The easiest way to do it is to work with leaves as with a stack. So we say that to make things easier, let me just make ants, which is like, in the beginning it is skeleton. And now we say that ants dot in place back of I and leaves dot back. And after that, leaves dot pop back. So we work with leaves as it is a stack, which we can like look at the topmost element and remove it. So here we did it. After that, we just return ants. So here we do not have any like leaves or something. We just need to construct a skeleton of the graph. Then second idea is the sorting part. I will not actually sort all the degrees, because actually the only thing you need is to differentiate 2 from 3 and 3 from at least 4. We do not need anywhere the d to be at least 5. So if it is at least 4, it is already the best we can hope for. So what I will do is I will make several buckets. So I will make vector int v2, v3, and v4. v2 will be the vertices of degree 2, v3 will be the vertices of degree 3, and v4 will contain the vertices of degree at least 4. Let's see how it goes. Again, I need this thing. So if di equals 2, v2 dot pushback of I. Else if di equals 3, then v3 dot pushback I. And else if di is at least 4, v4 dot pushback I. After that, we say that vector int v432, which is like in decreasing order. Initially, it is v4. Then I push back everything from v3 here. And after that, the same from v2. So now, vector v432 is functionally the same as this sorted vector. It is not sorted, because vertices of degree 4 can be shuffled in any order. But it doesn't bother us, because all we need is to discriminate between vertices of degree 2, 3, and at least 4. And leaves, of course. But leaves are already removed from the consideration. Now we can easily say that constant s equals v432.size, and we can begin considering cases. So the first case is s equals 1. Okay, so if s equals 1, then fail. So let's write that this is case 1, return nothing. Okay, now the second case, d1 is 2. Also, in the solution in the whiteboard, I used 1 indexation of the degrees. Here we will have 0 indexation. So if d of v432 0 equals 2, then we need to make a huge cycle. How do we make a huge cycle? I think I will write vector pair int answer, and I will have my answer in this variable. So here I say that we iterate over all vertices of degree 2, and we say that ans dot in place back of vertex I and vertex next after I. I would like to write something like this, and this is incorrect, because when you consider the last index I, which is size -1, if you add 1 to it, it will become size, and this is out of bounds. So actually you need something like this. You need to make it modular v432.size. But I don't like it. This is because you actually make a very expensive operation of taking modular some number. It is really slow. You don't need that. In this case, you only need to check if it is greater than n, and in this case, we go back to 0. And I have a pre-written function sum, which adds to number modulo sum modulus. So here I will just say v42.size. So I add I and 1, and if it becomes greater than this number, I subtract it. And now I can return the answer. Let's consider cases after that. So the third case, d2 is 2, then it is failure. We do not nothing. Don't do anything, I meant. Case 4 is s is divisible by 2. If I meant if s is divisible by 2, this is kinda where interesting part begins. So we need to divide all these vertices into 2 bamboos. I think I will just like use, this is the 0th, this is the first, This is the first, this is the second, this is the third, and so on. So like 0, 1, 2, 3, etc. How it can be written? First of all, we need to make the cycle. So we ans dot in place back of v42.0 and v432 first. We add it twice. After that, we go from 2 to s. I think I don't need size here. I can just put s. Now we iterate from the second till the s vertex, and we say that ans dot implies back v432 I minus second and v432 I. And that's it. This is the needed skeleton. Let's go on. Now we have the fifth case, which is d3 equals 2, and this is fail. Again, I have to follow the 0 index convention. So if I have d3 here, I need to write d2 here. So if it is 2, then I answer that it is failed. Next case is this one, s equals 3. In this case, the skeleton is just a triangle. Sorry, s equals 3. This case, I can actually copy paste this code because it is the same. It is totally the same. So the seventh case is d1 is at least 4. Seventh case is d1 is at least 4, and in this case, we need to make 2 bamboos of same size and then attach one vertex to d1. So this is the copy paste of this solution. But here we go till s minus 1. And v432 s minus first gets attached to the 0th vertex. So this will be our skeleton. Let's go on. Now s is at least 7. Let's look what we have here. This is also some sort of difficult case, but it is actually not very difficult. The beginning is the same. We construct this, but in the end we add this edge, but not to the 0th vertex, but to the second vertex, which is here. It cannot be seen, but I meant here. So this is the 0th, this is the first, this is the second. And I need to attach it to the second vertex. Okay. Now case number 9, which is d5 equals 3. So if d v432 of 4 is 3. And again, this is just the 5 cycle, which is written here. Finally, case number 10 is return nothing. All which is remaining is to check this solution. First of all, we will run it on examples and see if it works. Damn, I have already spent a whole hour on this. So, let's see. Yes, and a triangle, which is correct. Then no, then yes, and like a triangle plus 1, 4. So the best thing to do is to actually draw it. Okay, so what graph do we have? So 1, 2, 3, 1. After that, 1, 7, 1, 6, 2, 5, 3, 4. It is kind of understandable. It's just, it's correct if all the degrees are correct. Let's check the degrees. So we have here 4, 3, 3, 1, 1, 1, 1. 4, 3, 3, 1, 1, 1, 1. I guess it is correct. Let's go on. The next thing is this one. 5, 6, 5, 6, 5, 3, 6, 4, 3, 2, 4, 1. And here we have almost the same, but instead of these two edges, 1, 3 and 2, 4, I have 3, 2 and 1, 4. But 1 and 2 are just leaves, so it doesn't matter. I could do it in the other order as well. The next thing is no, and finally we have this strange graph. 3, 6, 6, 9, 9, 3. This is this triangle. And I think we will have to draw it again. So what do we have here? Here we have 9, 6, 3. 3, 8. 6, 7. 6, 5. 9, 4. 9, 2. 9, 1. First of all, it is obviously a correct answer if the degrees are correct, because it is flower-like. So here we have 1, 1, 3, 1, 1, 4, 1, 1, 5. Okay, so you see this and you think that your solution is obviously correct. Wrong. Actually, this didn't consider all the cases. Actually, it didn't consider much cases at all, many cases at all. Like, what did it consider? We can actually write with, like, debug output which cases were considered, but I think not very many. Not a lot. Still, we will send it, I think. Let's see if it is correct. Wrong answer, test 10. It happens. So one of our cases is incorrect. Maybe we can see it. Can we see it? Jury constructed a flower pseudotree while the participant not. This is not really possible to check. But we can check our solution. And again, we have several cases. I just need to look at them. So obviously the problem is that the skeleton is incorrect. Let's look at the skeleton. Or I think I will swap them. So here is the picture and here is my code. So I will shrink this down. Okay. So first of all, we do this, and this is fine. This is totally fine. After that, we do this, which is also fine. Okay, now goes the difficult part. Case consideration. So if s equals 1, then so the cycles are impossible. We return nothing. Then we consider the case that d1 is 2. And we require that s is at least 2. In this case, we construct an easy cycle. The third case is d2 equals 2, so this one. But d1 equal is at least 3. And in this case, we just cannot make a cycle. So we have to return nothing. Next thing to do is consider s divisible by 2. Okay, we do it. The fifth case is d3 equals 2. And this is impossible. Because we cannot make two branches, two bamboos of the same length. So in this case, we return no. Now, if s equals 3, we make a triangle. Then if this is at least 4, then we can do it. In case 8, s is at least 7, and we also do it. Hmm. Maybe here is the error. So s equals 5. All the degrees are 3. But last one is 2. Can an error be here? What's wrong with my camera? I don't think an error can be here. Can it be here? It turns out that something is made incorrectly. Again, what's the issue? It says that jury constructed a flower pseudotree while the participant not. But what is test? I think what we can do is to compare our solution with the tutorial and find maybe the case which we considered and we did it incorrectly. Somebody mentioned me. Okay. So when we printed fail, first of all, we printed fail when s equal 1. S is CNT here. It's not considered if s equals 1 actually in this editorial. Ah, it is said here, otherwise d1 is at least 2, is greater than 2, in which case there must be at least 2 such vertices. So, okay, this is fail, definitely. Ignore all vertices with di equals 1, as we can just hang them under all the other vertices. We did it. We definitely did it here. Yeah, we only considered vertices with degree at least 2. So if if all these degrees are 2, we can simply construct a cycle. And I do it in the third case. No, I do it in the second case, actually. So I say that d0 is 2. Yes, and I construct the cycle here. Okay, so now we consider that the second case is not the case. Now we say that now what we say is d1 is at least 3, and also d2 is at least 3. So this is the third case. Okay, let's go next. If C and T is even, we can make a cycle using d1 and d2, and I do it. So if S is divisible by 2, I do it. Okay, now S is odd. And then we consider case d1 is greater than 3. It's easy to see that we can hang. Maybe this case is incorrect. I think this case is incorrect because I can make a branching in d1. I can make a branching in d1. Okay, so this is where the problem was. So okay, let's fix it. So actually, let me think. This works if d1 is at least 4. So I think I should swap the case 7 and put the 7th case up to the place of the 5th case. Because if d1 is at least 4, then actually we can make this restructurization. Do we? Okay, let's fix it. So here we have, for example, we put it here. We say that now we have that d1 is at least 4. And here we only know that d2 is at least 3. But we actually only need d1 is at least 3. So here we have d1 is at least. Now we have that d1 is at most 3. And here we also have that d1 is at most 3. Okay. Sounds okay. Okay, so we need to put the 7th case here. Let's try and submit it again. I hope that it works this time. Wrong answer on test 1. I get it. So here I should say that. Let me think. I should say that S is at most. Okay, let's fix it like this. Let's just fix it in this order. So when does it work? It works then when d1 is actually 3. So when D1 yeah, I get it. So in that case, we cannot use that S is at least 5. So we need to check that S is at least 5. So maybe we can just write S equals 3 here. Sorry guys, I messed it up. Now wrong answer, test 11. Okay, I think we need to do it a bit more like systematically. Yeah, let's reconsider some cases. We need to reconsider cases 5, 6, and 7. So now what we know is these statements. What we can definitely say now. Hmm. Okay. Let me do it as I said earlier. So here I have sum of di is at least, or is equal to 2n. S is at least 3. 2 is not divisible by s. D2 is at least 3. And now I say that D3 equals 2 and S equals 3. Okay? No, I don't like it. I don't like it. I want to start with case 6 because this is most obvious thing to do. So let's assume that S equals 3 and D3 equals 3. Okay, in this case I make this triangle. Now sixth case is as follows. It says that sum of degrees is 2n, s is at least 3, 2 does not divide s, d2 is at least 3, and either, I will write it down below, either s is at least 5 or d3 so sorry, here I need that d3 is at least 3. Okay, or d3 is equal to 2. So this is what we know. And now I want to consider this case. This case which is saying that I think the lower case. Let's consider the lower case. Okay, in the lower case we say think it becomes something like a logical exercise. Okay, let me try, for example, what is this case about? Actually, I think this case is about d1 being equal to 3. So no branching in d1, no branching in d2. And also, but I already considered this branching here, didn't I? Ah, this is d1 at least 4, I get it. Okay, no, I want to consider the case 7. So d1 is at least 4, and s is at least 5. In this case, I do this thingy and add one vertex here. So the 7th case. Now it becomes harder because of the logic problems. So sum of di is 2n, s. And here we have something strange. Let's rewrite it. d2 is at least 3. Also we know that s is at least 5 or d3 equals 2. And also we know that d1 is 3 or s equals 3. Let's think how we can rewrite it. So if s equals 3, then d3 equals 2. Okay, let's now write this case, which is s equals 3. I think we can actually... Sorry guys, I will do it one more time, but I want to keep this order of the cases. Actually, I see that in this case we need... Let me like... do... Sorry, like something like this. Then okay, I should cut it. Can I cut it? I can only copy it. Why can't I cut it? I can copy it. Okay. Okay, and finally, I want to move this down. Okay. Now, what I will do is I will rewrite these cases. So again, let's rewrite what we know and what we imply. So here we do not know anything, and we just want to say that s equals 3 and d2 and d3 equals 2. So this is the 5th case. S equals 3 and d3 equals 2. Okay. So in this case, actually, this is a failure because we need to put the d3, the first and the second here. And now one of So after that there will be no branching, because here we have 3 and 3, and after that we have 2's. And since we have no branching, the depths will be different. So here we definitely have a fail. So what I was wrong about is what we now know here. Now we know here that S is at least 5, or D3 is at least 3. And now I consider case that S equals 3 and D3 is at least 3. In this case, we can use the triangle. So now here in the 7th case, what do we know? We know that either so first of all we know this, and also we know that S is at least 5, or D3 is equal to 2. Actually, in these two cases, the right thing cancels out. So we know either S is at least 5 and something, and we know that S is at least 5 and not something. Yeah? This simply means that we know that S is at least 5. Okay, we're right. S is at least 5. S is at least 5. And since, so we can just put it here, I think. Okay, now, since S is at least 5, we can check that D1 is at least 4. Okay? Hmm. And if D1 is at least 4, then no, this is not green, it should be black. D1 is at least 4. In this case, we make this jellyfish. Okay. Now, I think we have the problem, because here, I think, in the 8th case, that we know that S is at least 5. Yes, 2 does not divide S. Fine. We don't know that D3 is 3. Yeah, we don't know that D3 is 3. Hmm. Okay, I get it. Again, I messed up one more time. So we don't need here that S equals 3. What we need here is that D1 is equal to 3. Yeah, why? Because, again, if D1 is 3, then there is no way to make a branching. And actually, I used here that D1 is 3, and I didn't have any branching. This is where I messed up, because I wrote something else. Okay, so let's write it here. Now we have that D1 is at least 4, or D3 is at least 3. And now we say that if S equals 3 and D3 is at least 3, we can make a triangle. Yes, we can do it. Okay, here we have something more terrible. We have two conditions. That first of all, D1 is at least 4, or D3 is at least 3. And the second thing is S is at least 5, or D3 equals 2. And here I say that I need that S is at least 5 and D1 is at least 4. In this case, I can make the jellyfish. So what then? In the 8th case, let's look at what I have. So sum of di is 2n, s is at least 5, 2 does not divide s. Why again s is at least 5? I don't know this. I know that s is at least 3, of course. 2 does not divide s, and d2 is at least 3. And we have 3 conditions, 3 ors. d1 is at least 4, or d3 is at least 3. S at least 5, or d3 is equal to 2. And finally, S equals 3, or g3 is at least 3. So let's look at these two things. We know that this is true or this, and this is true or this. We can rewrite it. We can rewrite it as follows. We know that S equals 3 and d1 is at least 4, or d3 is at least 3. Okay, what about this thing? So if d3 is at least 3, then S is definitely at least 5. So maybe I can rewrite it like this. So is this equivalent to what I had? So let's check all 3 conditions. Is it true that d1 is at least 4 or d3 is at least 3? Yes, it is followed from here. Is S at least 5 or d3 equals 2? No, let's also add it here. And d3 equals 2. So let's come from the beginning. Is d1 at least 4, d3 at least 3? Yes. Is S at least 5 or d3 equals 2? Yes. Is S equals 3 or d3 is at least 3? Also yes. Oh, what now? Can we do it in the opposite direction? So if So can we do it in the opposite direction? I know how it can be done properly. So it's like the truth table. Let's make a table of all possibilities, and we will eliminate the wrong ones. So we have d1, we have d3, and we have s. And we have 8 different possibilities. So d1 is at least 4, and d3 is at least 3, and s is at least 5. Then s equals 3. After that, d3 is equal to 2 and s is at least 5. Then the same goes here. And finally, 4 things about d1 being equal to 3. Okay. Sorry for this mess. I get it. Actually, here we can also eliminate one possibility. Let's write it like this. So here we have s equals 3 or d1 equals 3. Why is it the case? So if s equals 3, we also are unable to make a branching because we just simply do not have enough vertices of degree at least 2. Yeah, so there are 2 pictures actually. First picture is this, and the second picture is we have vertex of degree at least 4, then vertex maybe of degree 3, at least 3. But we have only one more vertex to make the branching. We can put it here, yes, but still this depth will be 2 and this depth will be 1, because we don't have any other vertices of degree at least 2. So here I can rewrite it as s at least 5 and this or this. And again, here we can write s is at least 5 and d1 is at least 4 or this. And here we can write again one more time s is at least 5 and this or this. So let's write it into a truth table. So initially all possibilities are possible. Let's now eliminate some of them. So we know that d3 is at least 3. Or let's start with the simpler ones. For example, s equals 3 or d3 is at least 3. This means that if s3 is at least 5 and d3 equals 3, this is impossible. D3 equals 2, this is impossible. So this is impossible and this is impossible. Okay, now d3 equals 2 or s is at least 5. So it is impossible that s equals 3. Sorry, I again messed up. It is impossible that this is true and this is true. Okay. Okay, the second thing, s is at least 5 or d3 equals 2. So it is impossible that s is equal to 3, but d3 is at least 3. So this is impossible, and this is impossible. And finally, this thing, it says that it is impossible that d3 equals to 2, and either s is small, so like this is impossible, and this is impossible. Or D1 is big, small. So like this is actually impossible. No, sorry. Okay, I think this is fine. So now we actually know the following, that D3 is at least 3 and S is at least 5. But then we have this case, I think. Don't we? Oh. Yeah, I actually missed it. I wrote it incorrectly. So it shouldn't be D3 is at least 3 here. It should be... Why did I write it like this? So here we should have or D1 equals 3. Sorry. Let's again fix everything. So let's put zeros. So we should put 0 when S is 5, is at least 5, and D1 is at least 4. So S is at least 5 and D1 is at least 4. This is here and here. Now we should put zeros when S is 3 and D3 is at least 3. So S is 3 and D3 is at least 3. Okay, here. Next thing we need to do is to put when D3 is 2 and either S is small and S is small, or D1 is small. So now we have only this one, which is S is at least 5, D3 is at least 3, and D1 is 3. Which is enough to say that all these three things are 3. So this is true and this is true. Okay, I actually have done this, and I need to fix the case consideration. Oh. So actually, I only need here, let's rewrite. I only need here that G3. Oh no, I think no, I need everything. Do I? Don't I? Okay, we need everything. So here we say that S is 3. In case 5, S is 3. Let me put it like this. Or here we need that S is 3. Or G1 equals 3. And we return that we have a fail. So here we need that S is 3 and G3 is at least 3. Okay, and here, yeah, we have both this thing and this thing. Can we just state that G1 is at least 4? Yes, I think we can write it like this. So this is 4 and S is at least 5. And this would be correct. Okay, I kinda didn't test it, but I think it will now succeed. Because I checked everything. Yeah. Okay, this D1 actually needs to be D0. This is a stupid bug. Try again. What could we say? Fine. Okay, guys, if somebody of you didn't solve this problem during the contest, I fully understand you. This problem is a giant mess, and as you see, I was prepared for this editorial and still I messed up. Yeah, because this case should have said that D3 is 2, and also one of two additional conditions holds. And without that, it doesn't work, I guess. Still, we did it. Not without bugs. So thank you for watching.